Hello, everybody. Very happy to be here. My name is Jônatas, and I'm traveling from Brazil. So, yeah, that was a very special travel. And it's very special to me today. It's my birthday, so it's a great gift to be here. And I'm very, very happy for participating of such a high-level conference. I love all the talks. It's so amazing to see, and people are just rising the bar. So now I need to try to keep it, and yeah, I will try my best. So if you check my talk, the name is quite weird. Like you think like Ruby or SQL, and then like, oh, this guy is here just to complain about Ruby. And yeah, I'm not here to say that Ruby is slow. Ruby is not slow. So long story short, this is the main message. And and SQL is also not slow, so it will be a very nice comparison. And so the talk today will all be about the trade-offs of where do you process the data. So when you are talking about data, you are generally talking about I/O. And when you are talking about processing, it's CPU and memory. And so how do you keep it dancing and how you can make it happen? And I will start with an analogy. So it's quite fun. Like this is the Eon that is a tiger. So yesterday you have the puma, and today you have the tiger. And the tiger is quite nice and beautiful, and this is like the design from the designers of my company. But as I spent all my budget with the trip, I could not hire a designer. And then you will have this very weird tiger that's generated by AI. So my analogy is quite simple. So can you just imagine that someone call you and say like, hey friend, I'm just going to arrive at your house. And then you think like, whoa, that's cool. Let me do a watermelon juice. And then you think like, oh, yeah, I don't have the watermelon. So to carry the watermelon, I probably need some trolley bag that I can pull and push and do some stuff like that. And then you get prepared. And you start your walk. Like, it's not something that you can get in the 7-Eleven. Then you need to go to a real supermarket. And you go there. So you start your journey finding the watermelon that is good, it's tasty, and it's in the right point and sweet enough. And then you need to walk and have that tour in the supermarket, get attacked by all the chocolates and other things that you don't need, and then you continue, go straight to the checkout, wait it, and then you pay for it and just go home. So that's the thing, and then you get home. That's time for just blend it, right? So you slice it, you put into your mixer, and you blender and blend it, then you filter it, and then you have all the mess around. Like you need to have the trade-off of like cleaning, and then like your friends are already waiting for you, and you are rushing to finish everything, and then like you start like thinking, oh, I still need to get everything out. I have the things to clean, and finally you have your time with your friends. And that's the thing that you enjoy, you have the time there. And as you are a very nerd guy, later you start doing your personal retrospective and thinking like, where did you spend your time? It was so time consuming to have this juice done, right? And then you start doing your research, like how to juice faster. So this is hard, and it's a very hard thing. And then like you come to the internet and check what's the best juicer and watch YouTube videos about it. I will get the most expensive one, and then you just share it with your friends, like, hey, I'm analyzing, this is the best or that's the best. I'm not sure. And then you just discover that you are optimizing the wrong thing. And then like you start like thinking like and recapitulating, where did you spend your time really? So you spend your time in the supermarket, or did you spend your time just doing the juice, right? And if you just think a bit and you think like, oh, if I optimize 100% of 5 minutes, I will just get like 2 minutes, right? And then you think like, if you optimize 25% of 20 minutes, it's already 5 minutes that you had in the juice. So, and this is a lesson about like stop optimizing the wrong thing. So if you focus and you focus in the wrong part of your application, maybe you will be micro-optimizing. And that's the lesson learned here in this small analogy, right? So data processing is like juicing, right? So you are going to process something, you need to do this thing, and then shopping is your database round trip, right? So you need to go there and get your data, come back, and in the end you just want the juice, right? So you are carrying many more things and much more data than you need. And so the kitchen is your data processing location, like the place where you have your mixer. That's the hard part, and that's the place that you are going to optimize. So no matter how much time you invest on your juicer or in your kitchen, the problem is just like get the watermelon, right? And no matter what's the language or framework that you adopt, if you don't have like a good mindset about it, you discover that traveling is expensive. So less you carry, faster you go, right? So if you have a light backpack, you will go much more far and much more faster, and that's the point. So generally, when we are doing data processing, we are not like really getting out the raw data. We are really processing it, and we are juicing it, and we are reducing it in terms of size. So data processing is something like this. So here I put some quote that looks like I am intellectual, but this is a quote that is, I found it very interesting and so crazy. And this quote is funny, and I just want to say that I had a lot of fun generating this image, and it was quite nice to spend this time there. So now let's jump into the topic. So I already shared about the analogy, and my next step here is to talk about my adventures on data processing. So I will be sharing some benchmarks later, and also bring some kind of ideas of what I learned in this optimizing thing. So I am a kind of developer that don't code in the product, so I just have coding adventures, but I'm not in the front line. So I am always exploring code, but I am not like delivering a product. So this is more things I learned. So I work for TimescaleDB and at TimescaleDB is the extension, and I work there as a developer advocate. And when I joined the company, I am like working for more than 14 years now with Ruby. So I was like, oh, let me get the low-hanging fruit and do something with Ruby and Timescale. So I started creating some kind of like helpers to show how to use Timescale, and then I end up like packing it into a gem. So this is the coding adventures that I am going to explain. This is basically the first one. I will just clarify here some concepts. When I say here SQL, I am talking about PostgreSQL. Most part of the things are applicable to any database, but the thing is, like if you want to try some of these experiments with the other database, that will be similar thing. And TimescaleDB is the extension. It's a free extension for time series. And this is extension based in Postgres, so this is a C extension. And they have basically another extension that's like a sister extension that is named Toolkit. And the Toolkit is a group of like big nerds that are just doing math and doing everything in SQL there. So they are trying to create some of these ideas of like, hey, let's move a bit of like data processing to the database. So I was like, well, let me test it. And originally, my objective with the gem was just like, oh, let me create a wrapper that will be on Active Record and just like do everything that they need. And if I plug it on Rails, it will also be working with like DB schema, dump it correctly and everything. And then when the toolkit appears more stable, I was like, hey, let me try to also include the toolkit as part of the gem. And the toolkit is a bit different because it's written in Rust, and the other extensions are the other extension is written in C. We have a few extensions in Rust there, and I am also learning Rust, so I got like excited about this. So this is the thing that made me do that. So this QR code just links to a kind of article, and this article is about like the energy efficiency across several languages. So they get like C as the base, and then like you can see there like Rust is 3% more than C, and then you can see like Ruby very below there, like it's 69% more. And then you have aside another thing that is not the energy, but the time, and also the other thing is the memory. And in this article, you can see all the details, and then you can see how they build out this estimation of like what kind of consumption every language have. And then I was like, is it seriously like that it's so bad and that it's so more like somehow slow and everything? And then I was thinking, my analyses are very subjective, and I'm comparing oranges to apples, and like it's not very easy to do this kind of benchmark because you have a lot of things like if you warm up, if you have it in cache, and several things maybe will not be fair. And but this is what I got there, and every part of my experiment is open. So you can try to run it yourself and see what you find there. So the example that I will be using here is about volatility. So volatility is a very simple algorithm. It's used in a lot of different areas, like it comes from chemicals or physics, and people from financial markets use it a lot to just see what kind of stocks they will play and what are the most volatile stocks. You have more chance to win and lose money, right? And yeah, so here I'm just going to show like the base of like my database migration to generate my table. I'm using the timescale DB extension, so this is a hyper table. This is a core concept of timescale DB extension. So when you do a timescale DB extension, when you use it, you create this hyper table. You are just like linking your table, and it creates like an abstract table. So instead of like you have the big table, the original table, it's empty. And when you query some data, it goes to partitioned data, and then you can use like a chunk interval there. So in this case, like every day, it will generate a new table. So if you are inserting massive data, probably you can use like 1 day, sometimes 1 month or 1 year, and it will partition, create the subtables on demand, and this is quite useful. And then you don't need the ID, and you need to create a composed index for find data. If you have the ID, it will slow down the performance, so that's why it have it. So and then like, let's just imagine that you have this table and model, and then you order by the timestamp, and you are plugging the values of that you have in this measurement table. So it can be temperature or moisture or whatever. And then you build like this algorithm. So it's a simple sum of the delta between the values, and like you just iterate an array of values, and then you can use it, right? In SQL, I'm experimenting with the functional pipelines that this toolkit extension brings. So it brings the power of like functional programming to the database. So you can use the rows to concatenate several functions, and then you can do like much clearer, let's say, statements. Then you just like keep wrapping from bottom to top. You would need like a sum, absolutes, deltas of sorted values. So that's what it's doing. So you can just use the inverse order with the pipeline operator, right? And then, like, if you try it in SQL, it's a bit different. So this is the same thing in pure SQL in Postgres. So you need to have like a partition, and then you need to have like a know how to use partition, and you need to have a subquery to just collect the deltas and use the lag function to get the value between the deltas, and then that's the same thing. So I'm not going to use this. I just put it here just for the sake of comparison of plain SQL. So that's the thing. So let's jump into the benchmarks. And I'm going to seed some data here. So if I was going to use the active record to seed, it was going to be a few minutes. So I just use generate series. If you are not familiar with this is a very nice function. You can just put like a time interval or a range of numbers, and it will generate these numbers. So in this case, I am generating like data for 5 devices, and the numbers are random values between 0 and 80, and every 5 minutes for 1 month. So it's around 50K records, right? So with these 50K records, like this is not too much. I'm not like really testing a lot, but this is like enough to populate some memory and use it. So as I love scopes, I will just like throw it in a scope, throw my previous code, and the difference from the previous code from this one is that I am also using a hash map to group the volatility by device, right? So as the SQL is grouping by device ID, here it's the same code, but just grouping by device. This is almost the same thing. So we are collecting the deltas and just like creating the hash map for building this. And I will just have the same scope I shared before for the volatility. And this is the SQL version. And if I report, I will have something like this. So as you can see there, we have like the Ruby version is like 10 times slower, just for understanding. This is our local host, so no network involved. So it's and it's already 10 times slower. But it's not fair because I'm using Active Record, right? So Active Record is like just adding all the possible things to these like thousands of methods available there. So this is a very expensive thing, and I'm here to say that Ruby is not slow. Right, so the find out thing is the first thing that can be slowing down this code and make it not very fair, right? So let's just refactor it to C. So if I create a class that will process this, so I have like a volatility class, and then I have 2 methods. One method is just to delegate to the other methods and just rebuild the hashes and transform the volatility values. And then I need to change a bit of my SQL, right? So I need to get the group bys. So if you are not familiar with array ag, so array ag is a method, is a function from Postgres, and this is a native function from Postgres that you can use when you are grouping data. So you can aggregate all the values that are in the temperature of some device, and then you can just have them as a kind of hash map. So when you do like group with active record, and then you use aggregation, it will already generate a kind of hash map, which the key is the device ID and the value are the array of values, right? So this is the benchmark. So now I have one more step that I can compare. I can compare how much time I spend fetching the data and how much time I spend really processing the data, right? And then you can see that the values are much better, right? So you can see here like that the entire thing is like 743 milliseconds if I just do everything in Ruby, process you using active record, do that crazy thing. And then if you see the SQL that just do everything using the timescale DB toolkit function, it's 54 milliseconds. So you are getting like five keys and values from a hash map that's very fast traversing the network, and you have 116 milliseconds to just fetch the data in Ruby, and then you have 74 milliseconds to process. So if you think about this, this is very nice for Ruby. Like it's just 36% worse than the version that is written in Rust and do it in the database. So, and the problem is like the data is not in your memory. The data comes from the database. So the thing is on I/O. And then we can go deeper here. So where this 160 milliseconds is really spending. So and this was very cool because I don't know how much familiar you are with explain analyze, but explain analyze is basically a command that can run your query and show the query planner. So the query planner is the tool that run in the Postgres side, and it's a kind of calculator. So it goes to the memory, it goes to, some catalog of the database, and it knows like, oh, this page has X amount of bytes. I have any page that I need to go for. I will use this index or that, and this just calculates, oh, the best thing to do for this query is use this index and get this strategy to do this. So in the query planning, it's spending 70 milliseconds to plan, and then you have 36 milliseconds to be really executing the query plan, right? So in total, you have 54 milliseconds. So it's like exactly the same value that you have for processing everything in the database, right? But you have the 62 milliseconds remaining there. And this is the time that you have the DB serializing the information. And you also have the Ruby deserializing the information. So like considering that we have zero network here as its local host, so half of the time was just serializing data, right? So that's the point, and deserializing data from the memory. And yeah, so and then like you think, so it's 54 milliseconds to fetch and process the data, and that's not that different. So just recapping how the data travels. So when you do like your web server, it goes and queries some command, then you have like a SQL building a query plan, then the executor just executes the query plan, and then it serializes the data, pack into network packages, unpacking the other side, and then the language, the driver of the language, will need to unpack it and convert these strings to floats or whatever type of data type you have, right? So, and then you are spending much more time just doing this than like really sending the data. And I didn't find a good place to fit this, but this is a very interesting map that shows, if you check there in the top, you have the year. So as the years passed, the hard disk is getting really fast. So I'm not touching the hard disk part. We would have another conversation about like indices and things that could be improved in this side of like accessing the hard disk. But let's just zero this thing. Just think that we can skip it for now, but you see that it comes from several milliseconds to like nanoseconds now, and this is really, really interesting. And I have some slide here that is sharing research from Citus, and Citus is another time series database based on Postgres. And this is interesting because this is an estimate based on Fermi problem. So Fermi is a kind of guy that tried to like solve big problems that is hard to solve, and like, hey, how can you estimate things that you never get like a very closer value? So this article is very interesting because it's like, well, let's imagine some context where you have a hardware and you have like a good hardware, you have some cache ratio in your database, 99%, and then like how many rows in average I should be reading. So, and this is saying that you should be reading 1 million rows per second in the database, and considering you have like 100 megabytes connection, and in average your row is 100 bytes, right? So, and then like this is an estimation. This is like an approximate number that can guide you if you like, well, I don't know if this is fast or not. So this is a kind of like way. And this article is quite cool to get you there, to get you understand these values and then like maybe adapt it to your need. So this is a very interesting thing. So like let's just think a bit about the data pipes workflow, right? So depending on the processing, the location that you are going to process your data, you need more bandwidth. So if you process your data in the front end, you need that large pipe that will come from the database, that will have all the information traversing to the web server and in the back end, and then you need to traverse everything from the front end and then do something on the DOM to really render it in the client, right? And then if you do it in the back end, you will just like have a funnel there, like, hey, yeah, it comes until the back end, and in the front end, I'm just sending less data. My view is lightweight and everything. And if you do it in the database, you need a very small pipe because you are just processing and sending the data that you are expected to send, right? And this is a trade-off, right? So I put here some CPUs, like something to remember. So if you process in the front end, you not have anything, but a lot of things from the front end to be processing. And if you process in the back end, the same, like you are going to overload your server. And if you process in the database, you also have this CPU cost in the database, right? And so this is one kind of example. I'm also going to show one example that is alive. Let me just find a way to move here. Yes. So this is a downsampling algorithm, and in the top you can see. I need to get here. In the top you can see SQL version. In the bottom it's a Ruby one. I have like in average 400,000 records per table here. And this downsampling algorithm is a bit more complex, but you can see the difference here. So for example, let me get San Francisco, and then you can see here it's already loaded, and then like a few seconds later you see the Ruby. So it's processing everything in like less than a second in SQL, and then you have like 3 seconds in Ruby to process, and you have some extra time to downsampling. So you can see the green part is the downsampling. So processing is not really the problem. Like Ruby is fast, like, and it processes really fast, like if you have the data there. And it's all local. And here I'm using like an infinite scroll. So if I reduce here data, now I have like only 96,000 records. And the difference is reducing because you have less data throwing and flowing from the pipes, and then you can see that less data, everything is easy, right? You cannot see the difference, and if you have a lot of data, you will see a lot of difference. And yeah, so this is a small example that I am trying to digest all these things and trying to see like what are the edges. So the thing is all about like how much you are dragging through the pipes and how much you have to bring, right? So and in the end, Ruby is not slow, right? So Ruby is quite fast. You can see like it was not the bottleneck. The bottleneck is the I/O, and depending of your application, your application is bounded on I/O or it's bounded on CPU, and then you need to find your way to balance it and to prioritize where you can optimize it, right? So that's the main idea. And yeah, so that's all I have. Time to go. And I am living the future here. In Brazil, it's in the past. And yeah, I was just saying, like, it's 5 a.m. in Brazil, so it's quite funny to see. And so thank you very much. And yeah, that's it.